You know, those moments, right? When a totally new idea just clicks, a different way to solve something that feels obvious afterwards.
Uh-huh. Like, why didn't we think of that before?
Exactly. Now, what if an AI could do that? Not just follow our instructions, but actually invent better ways, fundamentally better ways.
Well, it's interesting, isn't it? Because for so long, inventing new algorithms, that felt like a purely human thing. You know, intuition, experience.
Right. But that's exactly what we're digging into today. We're looking at Google DeepMind's AlphaEvolve. They call it an evolutionary coding agent.
Okay, evolutionary coding agent. So it's an AI, using Gemini, those big language models.
Yeah, powered by Gemini, and it's working within this kind of evolutionary framework.
Like Darwin, but for computer programs. Generation, mutation, selection, that sort of thing.
That's the idea. But it's not just random changes. It's using Gemini's smarts to suggest intelligent mutations, to genuinely discover new algorithms.
So it's not just writing code faster, it's finding entirely new ways to compute things. That does sound like a shift.
It really does. Because like you said, algorithm development has always been this slow human process, decades sometimes.
Yeah, building incrementally. It makes you wonder what we might have missed along the way. Entirely different approaches, maybe.
Exactly. And that's the promise here. So our mission for this deep dive is to figure out how big a deal AlphaEvolve really is. We've got some great sources, timelines, briefings, a glossary even.
Good range of material, then, to see the whole picture from the concept down to the nuts and bolts.
And one achievement really jumped out at me. AlphaEvolve actually beat a 56-year-old benchmark in matrix multiplication.
So 56 years. Wow.
I know. In computing terms, that's basically forever, right? For half a century, the best human minds didn't crack this specific limit, and now AI has.
That's wild, especially for something like matrix multiplication. Strasson's algorithm from '69, that's been the standard for complex matrices for ages, a real landmark.
And this isn't just theoretical either. It's apparently having a real impact inside Google already. Big efficiency gains, we'll get into that too.
Yeah.
So let's start there. What exactly is AlphaEvolve? How does it perform this algorithmic magic?
Right. So in essence, it's an AI system. It uses the Gemini LLMs, the ones good at understanding and generating text and, importantly, code. And it uses them to drive this evolutionary process.
To discover and optimize algorithms.
Exactly. It's not just taking instructions, it's actively hunting for new, better ways to solve problems.
Okay, so less code monkey, more inventor. Let's break down that evolutionary loop you mentioned. Darwin for programs.
Yeah, think of it like a 6-step cycle. First up, problem definition and initialization.
So a person starts it off.
Yeah, a human expert. They define the problem, provide a starting algorithm, could be something basic, and this is really crucial, they provide the evaluator.
The evaluator. Okay, what's that? Sounds important.
It is important. It's basically a program itself. It acts as the objective judge. It checks any new algorithm AlphaEvolve creates and gives it a score.
A score based on what? Speed? Accuracy.
Could be anything you define. Speed, correctness, resource use, whatever matters for that problem. It's the hard metric AlphaEvolve uses to know if it's getting better.
So the human sets the goalposts and the measuring stick. Got it. What's step 2?
Step 2, program database and prompt sampling. AlphaEvolve keeps track of all the algorithms it's tried. It picks some promising ones, the parents, from this database.
Right.
And then it constructs detailed prompts to feed into the Gemini LLMs.
Ah, the instructions for the AI. What goes in those prompts?
It's pretty detailed. The parents' code, obviously, the context of the problem, feedback from how previous versions performed, and even hints about what kind of changes might be useful.
Like nudging it in a certain direction.
Sort of, yeah. Which leads to step 3. LLM-powered code generation and mutation. This is where Gemini gets creative.
Okay.
Based on that prompt, the LLM suggests changes, often as diffs.
Diffs, like programmers use.
Yeah.
Showing the changes.
Exactly like that. Add this line, change that one. It focuses the changes. And they might even use different Gemini models here, you know, like a faster one, Gemini Flash maybe, for lots of small explorations, and then the more powerful Pro for bigger, trickier changes.
Makes sense. Tailor the tool. Okay, so we've got a new candidate algorithm. What's next?
Step 4, automated evaluation. The new algorithm gets tested by that evaluator we talked about.
The judge steps in.
Right. Does it work correctly? How fast is it? How good is the score? This is the critical feedback.
Got to make sure it's not just producing nonsense code.
Precisely. Then, step 5, selection and population update. Based on those scores, the best algorithms get selected, They become the parents for the next round.
Survival of the fittest code.
Kind of, yeah. And the system tries to keep a diverse population, too, so it doesn't just get stuck optimizing one path too early.
Avoids getting stuck in a rut. And the last step.
Step 6 is just iteration and convergence. The whole cycle. Generate, evaluate, select repeats. Maybe millions of times.
Millions. Wow.
Yeah, until it hits the target performance, or maybe the improvements start to level off.
That's quite a process, an automated discovery engine. You really stress the importance of the evaluator earlier. Why is it so fundamental?
Because it's the only way AlphaEvolve knows what good means. It's the human expert saying, this is the target, measure success like this. Without a really solid, automated, efficient evaluator, AlphaEvolve is flying blind.
You can't learn if it doesn't have a clear test.
Exactly. If you can't write a good test, you probably can't use AlphaEvolve effectively for that problem, which also implies, it might struggle with problems where success is fuzzy or subjective.
Right. Needs clear, quantifiable goals.
Mm-hmm.
Okay, that makes sense. So we've got the how. Let's get to the what's. That matrix multiplication result, why is that such a big deal?
Okay, matrix multiplication. It's absolutely everywhere in computing. Training AI models, scientific simulations, graphics. It's fundamental.
And the standard way is n-cubed operations.
Roughly, yeah. Which gets computationally expensive really fast when n gets large.
They're not great for big data, big models.
Not at all, which is why finding faster ways is huge. Back in 1969, Volker Strassen found a way to do 2x2 matrices with just 7 multiplications, not 8.
Okay.
And if you apply that recursively, like to a 4x4 matrix, Strassen's method takes 49 multiplications. And for complex valued matrices, that 49 was the best we had for, well, decades.
49 multiplications. And that stood for 56 years, you said, for complex matrices.
That's right. For the kind of numbers we typically use, real and imaginary parts,
Right.
characteristic 0, mathematically speaking, 49 was the number to beat. It just shows how hard optimizing these core operations can be.
Until AlphaEvolve found a way to do 4x4 complex matrices in 48 scalar multiplications.
Exactly. Just 48.
Now, saving one multiplication?
Yeah.
Does that really make a huge difference?
It absolutely can. When these calculations are done billions, maybe trillions of times inside a big AI training run or a simulation, saving even one operation per small block adds up.
Ah, okay. The scale makes the small difference significant.
Precisely. It's like finding a tiny shortcut on a journey you take millions of times. It saves a lot of time overall. It suggests the AI found something non-obvious, a construction humans missed.
And this result, the 48, it's been checked out. Verified.
Yes, critically important. Independent researchers are on it. There's even a public GitHub repository, files basement AlphaEvolve matrix mul verification, where people are implementing it, testing it.
That's good. Open scrutiny, what are they finding?
They're confirming it works. It's correct, numerically stable for both real and complex numbers. They've even used things like quantum random matrices for testing, really pushing it. And they're trying to understand the underlying math AlphaEvolve found.
That's fantastic. Building trust in the AI's discovery.
Absolutely. Though it's worth noting, just because it has fewer multiplications doesn't automatically mean it's faster in every single practical implementation right away.
Oh, why is that?
Things like memory access patterns, how data moves around on the chip, that also affects real-world speed. So the initial code might need further tweaking to beat optimized Strassen on specific hardware.
I see. So the theoretical advantage is clear fewer operations.
Yeah.
But getting the practical speed up needs careful implementation.
Exactly. The potential is there, but realizing it fully is the next step.
Okay, so just to sum up the matrix part. Standard is 64 ops for 4x4 complex. Strassen got it down to 49 and 69. And now AlphaEvolve finds 48. That's a definite jump after a long, long time.
It really is. Shows it can tackle these really fundamental, long-standing challenges.
Okay, but it's not just solving math puzzles, is it? You mentioned real-world use inside Google. That sounds pretty significant.
Oh, definitely. It's not just theoretical. They've put it to work in some key areas. One big one is LLM kernel optimization.
Using the AI to optimize the AI. Makes sense.
Totally. Training models like Gemini is hugely compute-intensive, right? And matrix multiplication is right at the heart of it. AlphaEvolve looked at the Palace kernel, that's a specific bit of code doing matrix math for Gemini training, and it achieved a 23% speed up for that kernel.
23%. That's huge for a core component.
It really is. And that translated to about a 1% overall reduction in Gemini training time.
Okay, 1% overall might not sound massive, but for Training runs costing millions and taking weeks.
Exactly. That 1% is incredibly valuable, saves serious time, serious resources, serious money. They also got big speedups up to 32.5% for another key bit called the flash attention kernel.
Wow. So AI is making the AI that powers it faster. That feels like a feedback loop.
It really does, a virtuous cycle.
What else? Any other big applications?
Yeah, another major one is data center resource management, Google's Borg system.
Ah, the system that schedules everything in their data centers. That must be mind-bogglingly complex.
Unbelievably so. AlphaEvolve came up with a new heuristic, like a rule of thumb for scheduling compute jobs. And apparently, the AI's heuristic isn't just better, it's actually simpler than the old human-designed one.
Simpler and better. That's impressive. What was the impact?
An average 0.7% recovery of Google's worldwide compute resources.
0.7%. Again, sounds small, but at Google's scale.
That's absolutely massive. Huge savings in compute, power, cost. And this AI-generated scheduler has been running in production for over a year.
A year. So it's reliable.
It seems so. And apparently the code is human-readable, which is a big plus for the engineers maintaining it.
Right, not some incomprehensible black box. That's key for practical use. Any other examples?
One more mention is hardware design. For their TPUs, the tensor processing units.
The custom AI chips.
Yeah, designing those is super intricate. AlphaEvolve suggested a rewrite for a critical arithmetic circuit in Verilog, the hardware language. Functionally the same, but simpler.
So it's contributing at the hardware level, too.
Seems like it. Suggesting optimizations right down at the circuit design level.
Software, resource management, hardware design. And wasn't there something about unsolved math problems, too, outside of Google's direct needs?
That's right. They applied it to over 50 open problems in math and computer science.
Open problems, like things researchers are actively working on.
Exactly. And in about 3/4 of the cases, AlphaEvolve matched the best-known human solutions, which is pretty good validation.
Yeah, matching the state of the art.
But even better, in about 20% of cases, it actually improved on the best-known solution.
It found better answers than humans had managed for established open problems.
That's what they report. One specific example given was the kissing number problem in 11 dimensions.
Okay, kissing number. Sounds interesting.
Yeah. It's about how many spheres you can pack around a central sphere without them overlapping. A tricky geometry problem. AlphaEvolve found a new lower bound, a configuration with 593 spheres touching the center one in 11D. A step forward.
Okay, so faster AI, optimized data centers, better chips, and pushing the boundaries of pure math. It's pretty versatile.
The range is definitely impressive. It highlights how powerful this core approach is, using LLMs to evolve code against a clear evaluation metric.
Now, DeepMind had AlphaTensor before, right? That also tackled matrix multiplication. How is AlphaEvolve different?
Good question. They're related but distinct. AlphaTensor was highly specialized, built just for finding matrix multiplication algorithms using reinforcement learning, framing it as a game, and tensor decomposition math.
Laser focused.
Very. AlphaEvolve is much more general purpose. It uses the LLMs and that evolutionary loop we talked about, and it can tackle a wider range of coding problems if you can give it that good evaluator.
So specialized versus generalist.
Yeah.
And what about the actual matrix results? You mentioned AlphaTensor found 47 steps.
It did find 47 for 4x4, but that was in a specific mathematical setting called finite fields, modulo 2. It's like a different set of mathematical rules. Still important, but different. AlphaEvolve's 48 is for the standard complex numbers, characteristic 0, which is arguably more common in many scientific and engineering applications. The paper explicitly calls this out as solving an open problem in that domain.
So different kinds of math. 47 for finite fields, AlphaTensor, 48 for complex numbers, AlphaEvolve.
Exactly. And the fact that the more general AlphaEvolve got this breakthrough in the complex domain, an area AlphaTensor also looked at, well, it might suggest these generalist LLM-driven systems are becoming incredibly powerful, maybe even catching up to specialized systems in some cases.
Interesting. The trend towards more flexible AI continues. Okay, but it can't be perfect. What are the downsides, the limitations or challenges with AlphaEvolve?
Definitely limitations. We keep coming back to it, but that evaluator dependence is number one. No good evaluator, no good results.
If you can't define success clearly, it struggles.
Right. Second, high computational cost. Running this thing, potentially millions of LML calls, millions of tests. It takes serious hardware, serious resources.
Not something you run on your laptop.
Not even close. Then there's the potential for, let's call it, alien logic. Sometimes the solutions it finds might be super optimized, but really hard for humans to understand why they work.
Hard to verify, hard to build on.
Could be. Makes maintenance tricky too. Also, its scope is limited. It works best on problems solvable with code. Abstract conceptual problems, maybe not its strong suit. And finally, validation. Always need independent checks from the community.
All fair points, important caveats. But that virtuous cycle idea is still really compelling. Can you just quickly recap how that works again? AlphaEvolve improving Gemini.
Sure. So AlphaEvolve optimizes core code like the Palace kernel used in Gemini training. That makes training Gemini faster and cheaper.
Right.
Faster, cheaper training means Google can potentially build bigger, better Gemini models more easily. And those improved Gemini models could then make the next version of AlphaEvolve even smarter at finding optimizations.
Ah, I see. The AI improves the tools used to build the next generation of the AI.
Exactly. A positive feedback loop that could accelerate progress.
And this didn't come from nowhere. It evolved from FunSearch, an earlier DeepMind project.
That's right. AlphaEvolve is like FunSearch on steroids, basically. FunSearch also used LLMs for discovery, but AlphaEvolve is way more capable.
How so?
It handles much bigger code chunks, hundreds of lines, not just small snippets. It works with any programming language, not mainly Python. It can run much longer, more complex evaluations on accelerators. It uses the newer, more powerful Gemini models. And it can optimize for multiple goals at once, not just one.
So a really substantial upgrade across the board. Much more powerful and flexible.
Definitely. A big step up reflecting how fast the field is moving.
Well, this has been incredibly insightful, a really fascinating look at AlphaEvolve. So to quickly recap, it's AI discovering fundamentally new algorithms, not just writing code. It's broken a 56-year-old barrier in matrix math, and it's delivering real-world results inside Google, faster AI training, better resource use.
Yeah, it paints a picture of AI shifting towards being a creative partner in discovery, finding things humans might miss.
It really does. And it just leaves you wondering, okay, if AI can do this for matrix multiplication or scheduling, what other really hard, long-standing problems out there are just waiting for this kind of approach? What does this mean for science, for engineering? Feels like we're just scratching the surface. What's the big question listeners should maybe chew on after hearing all this?
I think the really profound question it raises is about the future of human ingenuity itself. If AI can start autonomously finding novel, efficient solutions like this, how does that change the role of human experts, researchers, scientists, engineers? It's not just about speed anymore. It's potentially about rethinking the whole discovery process, isn't it? How do we best collaborate with these incredibly powerful new tools in that search for knowledge?